Yeah, we need to keep going. Okay, so the presentation today is the strength of Earth's magnetic field from pre-pottery to Pottery Neolithic in Jordan. And this is a paper that's been just published on PNAS, and it's a collaborative work with the Scripps Institution of Oceanography, University of San Diego, Tel Aviv University, the INGV. I'm sorry if you already know these things, but it could be useful to remind that this paper is on a discipline that is called Archaeomagnetism, which is the collaboration between archaeology and paleomagnetism. Paleomagnetism is based on three physical phenomena. The Earth as a magnetic field. This field changes in direction and intensity over time, and magnetic minerals magnetize according to the existing magnetic field and preserve their record over geological times. How we study the magnetic field, we can rely on direct measurements when we have them with satellites or shipboard data. But for the geological past, we need to rely upon materials which recorded the magnetic field when forming. For instance, these nice cave sediments or marine or lacustream sediments, but also volcanic rocks and also archaeological sites. This is a brick wall, for instance. The advantage of the first two is that you have a continuous record of magnetic field, whereas volcanics and archaeomagnetics, you have a snapshot of the field. But there are other advantages that you can recognize the absolute value of the magnetic field strength. Why it's important, the Earth magnetic field strength is a protective shield against solar radiations, and it modulates the cosmogenic isotopes production. So varying the intensity of the geological past, it will also change the efficiency of such shielding. And in some papers suggested they also have had impact on the evolution of life on Earth. Arc intensity is a way we study intensity, absolute intensity from archaeological objects. In this image here, you see a nice oven with potteries burning. And so the advantage is you can study the value of magnetic field from these walls in form of thermal remagnetization. And usually potteries and other objects will not be in situ, so you can only study the intensity from them. And of course, the feasibility of an arc intensity study is limited to the availability of well-dated materials. But when you don't have well-dated materials, you can use archaeomagnetism as a dating tool. So pottery and other materials such as ovens and earth are really common materials studying archaeomagnetism, whereas other materials such as stone tools are much less studied. These are manufacts that are really much older than the use of ceramics, for instance. And some scientists, some archaeologists think that these siliceous rocks, chert, were heated to facilitate the manufacture of blades and knives in the process called knapping. And we call it burnt chert, we call it flint. This is a nice picture of a blade that I'll talk about later on. So the flint applied used for arc intensity, it was a first experiment by Carancho in 2014, studying in the lab. They heated some materials and then see if they could gain any, retain any reliable magnetic signal, but that was not the case for flint. In two other studies, recent studies, the authors did obtain pole intensity from a Neolithic Italian and a Paleolithic Israeli cherts, so it's promising. The discrepancy between these two studies, these two aspects, is that maybe chert show different degrees of enhancement of their magnetic property when it's heated up, above 400 to 500 degrees due to new magnetite formation, which is the best of magnetic recorded magnetite. Now back to the aim of this study is we want to obtain new arc intensity data from a period of Neolithic called Pre-Pottery and then Pottery Neolithic. We have available ceramics and flint from Jordan. And we want to understand the behavior of the Earth magnetic field over this period and expand the applicability of archaeomagnetism as a independent dating tool. The area is very interesting for us paleomagnetists because the Middle East is the region where where Genevieve 2003 found the so-called Levantine Iron Age anomaly. It's a time when intensity was very, very high, 160 zeton per meter, and in a matter of a very few years. And this anomaly is not accounted to our recent knowledge of the magnetic field dynamics. And yet, data showed this anomaly. Just to give you a reference, today is around 75 zeton per meters, just as a reference. So the first thing we did was to see what the state of art is. So there is a database called Geomagia, where you can query for the data from, for instance, in this case, the Middle East, and in a radius, in this case, 700 kilometers from the locality. And there were only 679 data points, and none of them was older than 7,000 BCE. You can see the area in the dotted red square. This that I told you about the Levantine Iron Age anomaly. There are a lot of data because it was really interesting, but we don't know much about the past. So first thing I did, it was to filter the available data according to FAIR principles. So data that could have associated a good geochronological dating. Data that were obtained with a method that is robust and had all the usual corrections for archaeomagnetic data, and the data needed to be accessible to be reprocessed using a consistent set of criteria, because different studies would use different criteria to select how good the data is. With these very simple criteria, 20% of the data were excluded. I'm going to show you now what we had available. We have 4 Neolithic excavations from a place in Jordan. It's called Wadi Fainan, and here are some examples. This is a statuine torso from Guahir, which is our oldest site. Radiocarbon dates around 7,500 BCE, and we had then some flint that I mentioned. Some blades from Wadi Fainan 01. They were very beautiful, and unfortunately I had to break it down for science, but it was worth it. And then we had ceramics from other 2 sites, Wadi Fidan 61 and Wadi Fidan 51, covering overall a time between 7,000 to 5,000 BCE around. In the lab, I had to cut them. Here is the poor blade cut, but I had to do it, sorry. I applied the method that is called the easy method. I won't go into detail. And I did 4 experiments in the lab using 2 different lab fields. I applied the usual corrections, the cooling rate and the ATRM correction, and the corrections were good. And overall, half of the sample gave a good value. For who works with archaeointensity knows that this is not a bad outcome. And the one that didn't pass the criteria were for alteration or multi-domain, so non-ideal magnetic behavior. Of the original 18 samples, 11 then are considered reliable. One thing that could be interesting for archaeologists is that we propose a test to check for firing efficiency in terms of how efficient is the firing into the magnetization. It's different from the Kuhn ratio, Königsberger ratio, because that's to assess a source of magnetic anomalies by comparing the remanent and the induced field. In this case, we have the natural remanentization and the susceptibility plotted. To the left panel, we have the firing efficiency ratio for all the samples, all the specimen analyzed, sorry. Whereas to the right, we have only the one that passed the selection criteria of the experiment. So finally, it looks like that you need a higher ratio to maybe have a TRM. And so now we can compare the data that they obtained in the lab to the current data sets. You can see here that the curves are models, are global and regional models, are based on sedimentary data, whereas these colored dots are other studies. So our lowest value is also the oldest value for the area is Guair, and then the other two values are Wadifidan 01 and 61. The values needed to be converted in DADM, and then we can compare them to the current data set. We can then interpret these results. They need to be confirmed, of course, but if that would be confirmed, we will have a rate of change of the magnetic field, which is comparable between Guair and Wadifidan 01, which is around 8,000 to 7,000 years BC, comparable to the preceding 500 years to the Levantine Iron Age anomaly. Whereas the other sites would confirm a time where the field was not very active in a way, varying around what's now the current value of the magnetic field. This is what is the conclusions for now. I presented to you 11 archaeointensity data from a period that was pre-pottery and Pottery Neolithic, and we demonstrated the potential and applicability of stone tools for archaeointensity study. I don't have to remind to archaeologists, but stone tools and flint are the most common material for the last 500 kilo years, and it can only now begin to be explored, and is a huge potential for applications there. And so in this study, the 4 archaeological excavations for Wadi Fainan region covered the beginning of the Holocene, and 2 of the data that we presented are the oldest of the Middle East, sorry. And we can expand that the data set of the to the early Holocene then. And in this way, we also expand the applicability of archaeomagnetism as a dating tool, and we propose a test for firing efficiency that needs to be further tested, actually. The paper and the work was picked up by the press, which was really nice. It's always nice to see collaboration of archaeologists and paleomagnetists also picked up by other publishers that deal with spreading outreach our science. And I will leave you with the website and the list of reference, of course. Thank you very much.
Thank you so much, Anita. Could you please stop the sharing screen? Okay.